Ever felt like those elegant system design diagrams make perfect sense on paper, but then you hit deploy and a whole new world of complexity just explodes?
Oh, absolutely. It happens all the time.
You're definitely not alone.
Yeah, man.
Today, we're taking a deep dive into the real-world deployment patterns of microservice architecture.
Yeah, getting into the nitty-gritty.
Our mission is to bridge that gap for you. How those clean, logical microservice views translate into the, well, messy, intricate physical realities of production system. We're zeroing in on exactly what you need to master for senior tech interviews.
Right.
By the end of this deep dive, you'll be able to confidently discuss scalability, intricate trade-offs, and real-world implementation, helping you navigate those interview discussions like a seasoned pro.
What's truly fascinating here, I think, is how we bridge that gap from the elegant design to the robust production-ready systems. It's where the rubber truly meets the road for any serious system architect.
Definitely.
And it's where interviewers can really separate those who just know the concepts from those who can actually build and troubleshoot them.
Okay, let's start by clarifying a fundamental distinction then. We often talk about microservices in a purely logical sense. Our invoice service talking to our order service.
Okay.
It looks so clean on a whiteboard.
Exactly. The neat boxes and arrows.
But what exactly does that logical view abstract away? I sometimes think of it like this. The blueprint of a house details the rooms and their functions. That's your logical view.
Mm-hmm.
But the actual house, with all its plumbing, electrical wiring, the hidden foundation, that's the physical topology. The logical view helps define business logic and service boundaries.
Sure, for modeling the domain.
But the physical topology is about the actual infrastructure where those services live and run.
And this raises a crucial point for system design interviews. When is simply talking about logical models enough? And when do you absolutely need to dive into the physical deployment details?
Yeah, that's cute.
A common pitfall, and frankly a warning sign interviewers look for, is when candidates assume their logical diagrams perfectly represent the production topology. That's a red flag.
Right.
You always need to consider physical deployment complexity and infrastructure requirements. While abstraction is incredibly useful for domain modeling, for defining business capabilities, it's simply insufficient when you're designing for a robust, production-ready architecture. It's really the difference between sketching a building and knowing how the beams will actually support the roof.
That's a great analogy. So with that foundation, how do we move beyond just a single instance to handle real-world loads and failures? What's the next big step in making our services resilient?
Well, that's where horizontal scaling comes in. You almost immediately move from one instance of a service to many.
Yeah.
This means you might have multiple instances of your invoice service running, maybe talking to multiple instances of your order service. Now, if we're using, say, HTTP-based API calls, the immediate challenge is how do incoming requests find the right service instance?
And how do services talk to each other without knowing every single address? Seems complicated.
Exactly. This is precisely where load balancers become indispensable. They sit in front and distribute incoming requests across those multiple instances.
Oh.
And that gives us both increased capacity and improved fault tolerance. If one instance goes down, the load balancer just routes traffic to the healthy ones.
And what's fascinating here is that it's not just about slapping a load balancer in front, right? I imagine there are critical choices and configurations.
Your choice and configuration of the load balancer are crucial. You'll encounter different algorithms, like round robin, which just distributes requests evenly, or least connections, which sends new requests to the instance with the fewest active connections. That's great for uneven processing times.
Okay, makes sense.
Or even weighted distribution, which is useful if some instances maybe have more capacity than others.
Right.
A key consideration, especially for stateful services, is session affinity, sometimes called sticky sessions. This makes sure a user's requests consistently go back to the same instance.
Why is that important?
Well, misconfiguring this can lead to really tricky intermittent errors, where a user's subsequent request hits an instance that has no knowledge of their previous interactions, maybe stuff stored in memory.
I can see how that would be confusing.
Yeah. And modern deployments also rely heavily on health checking, making sure traffic only goes to healthy instances. Plus, robust service discovery mechanisms to find those instances dynamically.
Service discovery, like a registry.
Kinda, yeah. And in some advanced setups, like with service mesh technology, that load balancing intelligence can even be moved into the service's runtime itself, handling a lot of that complexity transparently for you.
Interesting.
So a common interview question you might get is, how do you choose between different load balancing algorithms for microservices, and what are the trade-offs between stateless and stateful service design in this context?
Good question.
I remember once spending days debugging a weird customer complaint. Turned out it was a misconfigured session affinity rule causing inconsistent user experiences. Very subtle, very frustrating.
Ouch. Building on that idea of robustness,
Yeah.
then, what happens when we need to protect our system against, like, major outages? An entire data center going offline, say DC1 or DC2, we're talking true resilience here.
Right, you're talking about geographic distribution, distributing instances across physically separate data centers, or what cloud providers usually call availability zones or sometimes regions.
Okay.
And here's the surprising truth many engineers overlook. Cloud providers like AWS, Azure, or Google Cloud, they don't actually guarantee an SLA for a single machine or even a single availability zone.
Really? Not even a whole zone?
Nope. Which means a single zone deployment is simply not enough for enterprise-level SLA requirements. It's a critical red flag for production readiness.
Wow.
Multi-zone or multi-region distribution is practically mandatory if you need genuine high availability.
But there's always a but.
Always. This immediately brings up the CAP theorem. When you distribute across data centers, you will encounter network partitions eventually. It's inevitable. And that forces you to choose between consistency, availability, and partition tolerance. You can only strongly guarantee 2 out of the 3.
The classic trade-off.
Exactly. Plus, cross-data center communication introduces significant latency, which can definitely impact user experience.
Yeah, speed of light and all that.
Right. So you then need to carefully consider data synchronization strategies, consistency models, maybe eventual consistency is okay. And you need robust failover logic for both instance-level failures and entire data center-level failures.
A lot to think about there.
Definitely. So an interviewer might ask something like, how do you balance cost versus availability when designing multi-region architectures, and what are the practical implications of the CAP theorem for distributed microservices?
Good one. Okay, let's shift gears a bit to a classic microservices mantra. Don't share databases. We hear this constantly.
The golden rule.
The idea is that a microservice encapsulates its internal state, its data. But what happens when we have multiple instances of the same microservice? Do they each get their own DB? That seems complex.
That's a great clarifying question. And yeah, it's a point of confusion for many people. In a word, no. They don't each get their own database. Think about it. If you access any instance of your order service, for example, you expect to get information about the same order, regardless of which instance answers
Right, obviously.
So multiple instances of the same microservice can, and typically do, share a database without violating the don't share databases principle. The core of the principle is that the logic for accessing and manipulating that state is still contained entirely within that single logical microservice boundary.
So the anti-pattern is sharing a DB between different services, like order and invoice hitting the same tables.
That's the big no-no. Order service owns the order data, invoice service owns invoice data, and they talk via APIs, not by reaching into each other's database.
That distinction is crucial. Okay, so if multiple instances of the same service are sharing a DB, how do we then scale that database itself to handle the increased load from all those instances?
Good question. For scaling that shared database, a primary-replica DB strategy is very common, sometimes called master-slave, though primary-replica is preferred now.
How does that work?
All the write operations, inserts, updates, deletes, go to the primary node, and then read-only traffic is directed to one or more read replicas.
So you offload the reads.
Exactly. This frees up capacity on the write node and lets you scale your read traffic relatively easily just by adding more read nodes.
But there's a catch, isn't there? Consistency.
You nailed it. A common mistake, a definite warning sign in an interview or in practice, is treating read replicas as immediately consistent. Replication takes time.
Right, the lag.
Yeah, replication lag. You must handle eventual consistency in your application logic. Imagine a user updates their profile and then immediately views it if their read request hits a lagging replica.
They see their old data. That's bad.
Super confusing for the user. So an interview question might be, how do you handle read after write consistency in applications using read replicas? And what are the trade-offs between synchronous and asynchronous replication?
Synchronous being safer but slower.
Generally, yes. Asynchronous is faster, but introduces that lag potential. I've personally debugged scenarios where replication lag caused users to see outdated data right after an update. led to a lot of support tickets and a painful fix.
I bet. Okay, building on that database theme, what about the underlying database infrastructure itself? We could put multiple logically isolated databases, say one for orders and one for invoices, on the same physical hardware.
Like the same database server instance, maybe using different schemas or databases within it.
Or we could give each microservice its own dedicated infrastructure, its own server or managed instance. What are the pros and cons there?
This really boils down to a trade-off between cost and isolation. Shared infrastructure, putting multiple logical databases on the same physical box, obviously offers cost optimization.
Cheaper, fewer servers to manage.
Exactly, especially for things like licensing costs and maybe reduced management overhead if you're running things yourself on premises. But
Here we go again.
if that shared infrastructure fails, or even just gets overloaded,
It impacts multiple microservices. A single point of failure, or at least a shared bottleneck.
precisely. Dedicated infrastructure, on the other hand, giving each service its own physical or virtual DB server, provides much better isolation. Performance is more predictable. One service getting hammered is less likely to affect others.
But presumably more expensive.
Traditionally, yes. More servers, more management. Again, just to reiterate the anti-pattern. A definite misstep is sharing the same database schema or tables between different microservices. The correct approach remains the database per service principle at the logical level.
Got it.
But it's perfectly fine and often necessary for multiple instances of the same service to share their dedicated database.
Okay. And how do cloud providers change the game here? Does that dedicated approach become easier?
Oh, massively. This is where cloud providers truly shine. Managed database services like AWS RDS or Azure Database, Google Cloud SQL, they simplify the operational concerns hugely.
How so?
Things like backups, patching, software upgrades, setting up multi-availability zone failover. A lot of that is handled for you, often with just a few clicks in the console or an API call.
Takes away a lot of the operational burden.
Exactly. This makes provisioning dedicated database infrastructure on a per microservice basis far more cost-effective and operationally feasible than it used to be trying to do it all yourself on-premise.
Right.
And it also often gives each microservice team more autonomy and control over their specific database configuration and scaling, rather than being bottlenecked by a centralized, often overwhelmed shared DBA team.
More team autonomy, faster development potentially.
Potentially, yeah. So an interviewer might ask, how do cloud-managed database services change the economics of dedicated infrastructure? And what are the organizational benefits of giving teams full database control versus using shared infrastructure?
Interesting organizational angle too. Okay. Speaking of balancing cost and complexity, that brings us neatly to maybe one of the most practical considerations for any system. How it evolves through different environments.
Oh, yes. Environments, dev, test, staging, prod.
Exactly. From your laptop all the way to production. How do our microservices typically journey through these environments, and why does their physical topology often change along the way? This feels super relevant for interviews.
It absolutely is, because it directly reflects your understanding of real-world deployment pipelines and operational realities. Different environments serve different purposes, right? Development is for coding and quick checks. CI is for automated testing.
Pre-production or staging for near-production validation.
And then production, the real deal. Ideally, you'd want each environment to be an exact replica of production to give you maximum confidence that what works in test will work live.
But that sounds expensive.
It usually is. Running multiple full copies of a complex production environment with all the data centers, load balancers, scaled databases, it's often prohibitively expensive. Plus, you often want to tune earlier environments for faster feedback loops, not necessarily perfect fidelity.
So you might make trade-offs.
Definitely. For example, you might have just a single instance of each service running on your developer laptop. Maybe 2 instances running on the same machine in a CI environment just for basic integration tests.
Okay.
But then in production, you might have, say, 4 instances spread across 2 different data centers, like DC1 and DC2, with proper load balancing and failover.
So the expectation isn't always perfect parity across all environments then. That seems like a potential interview trap.
Exactly. And that's a critical mistake to avoid falling into the trap of saying, oh, all environments must be identical. That's often unrealistic. The correct approach, the senior approach, is to balance cost versus fidelity. You want increasing production-like characteristics as you get closer to production, but you accept differences earlier on. This inherently means the physical deployment topology of a microservice will change from environment to environment.
Right. Which leads to configuration, I guess.
Precisely. A crucial point is that environment-specific information like database connection strings, API keys, maybe the number of instances needs to be entirely separate from the deployed service artifact, the binary or container image.
The build once, deploy many times principle.
You got it. Which means another anti-pattern to steer clear of is embedding static configuration directly in the service artifacts. That's a huge red flag.
Why?
Because then you need different builds for different environments. It breaks the principle. You absolutely should use external configuration management for environment-specific parameters, build in at deploy time or runtime.
Like environment variables, config maps, secrets management systems.
Exactly. All those tools exist for this reason. So an interview question here might be, how do you design applications to handle variable deployment topologies across different environments? And what are effective strategies for environment-specific configuration management and secrets management?
Make sense? It's how we move past that classic developer joke.
It worked on my machine.
Exactly. Proper environment management helps solve that.
Or at least reduce it.
We've covered a lot of ground today seeing how these deployment concepts fit together. It's much more than just drawing boxes.
Definitely layers of complexity.
Now, let's really test that senior mindset we've been talking about. How about a few rapid-fire interview scenarios? Put you on the spot.
All right, let's do it. I'll pose them. You answer.
Sounds good.
Hit me. Okay, let's start with a conceptual one. Explain the difference between a load balancer and service discovery in a microservice architecture and how they interact.
Okay. A load balancer is primarily focused on distributing incoming network traffic, like user requests, across multiple healthy instances of a service. Think of it as the system's traffic cop, directing requests efficiently to avoid overloading any single instance and ensuring high availability.
Good. And service discovery.
Service discovery, on the other hand, is the mechanism. It's how a service finds the network location, the IP address and port of another service it needs to communicate with. It's like a dynamic real-time phone book for your services because instances come and go.
Okay, and how do they interact?
They interact because service discovery often provides the load balancer with that dynamic list of available and, importantly, healthy service instances. The load balancer then uses this information from service discovery to intelligently route the incoming request only to the correct, healthy instances, ensuring no traffic gets sent to a downed or unresponsive service.
Excellent explanation. Clear distinction and interaction. Okay, next one. Imagine a troubleshooting scenario. You're getting reports of intermittent connection issues to a shared DB from multiple microservice instances. What are the first three things you'd investigate?
Okay, intermittent BB connection issues. Tricky. First three things. First, I'd check the application-side connection pooling. Are the microservices properly configuring and managing their database connection pools? Maybe they're exhausting the pool, not returning connections correctly, leading to timeouts when new requests come in.
Good start. What else?
Second, I'd look for resource contention on the database server itself. Is the DB overloaded? Maybe too many queries hitting it at once from all these microservice instances. Check CPU, memory, I/O limits. Maybe look for long-running queries that are hogging resources.
Makes sense. And the third?
Third, I'd investigate potential network issues between the microservice instances and the database server. Even if both ends seem okay, there could be intermittent network latency spikes, packet loss, or maybe even a misconfigured firewall rule that's dropping connections sometimes. Network path issues can be subtle.
Great systematic approach. Application, database server, network path. Very solid. Okay, final one. A design question. You're designing a new critical microservice. What operational considerations would you prioritize from day one to ensure its reliability in production?
Day one for a critical service, reliability is paramount. Okay, I'd prioritize three main areas immediately. First, robust monitoring and observability. Second, comprehensive deployment orchestration. And third, built-in fault tolerance patterns.
Can you elaborate briefly on each?
Sure. For monitoring and observability, defining key performance indicators, request rates, error rates, latency like P99 latency right away, plus detailed structured logging and setting up distributed tracing so we can follow requests end-to-end across the system. You need visibility before things go wrong.
Absolutely. Deployment.
For deployment orchestration, I'd want automated, repeatable, and ideally zero downtime deployments from the get-go. Things like blue-green or canary release strategies with clear and tested rollback capabilities, no manual messing around in production.
Essential for critical services. And fault tolerance.
Yeah, for fault tolerance, I'd bake in patterns like circuit breakers to prevent cascading failures if a downstream service is struggling. Implement sensible retry patterns, probably with exponential backoff and jitter for transient network issues, and maybe even design for graceful degradation. Can the service provide partial functionality if a dependency is unavailable? Basically, assume failures will happen and design for them proactively.
Fantastic answer. Thinking about monitoring deployment and resilience right from the start, that's exactly the senior mindset.
That was a great simulation. Really puts these concepts into a practical interview context.
Yeah, helps solidify things.
So, to quickly recap the key lessons we've unearthed today, because we covered a lot. First, always remember that crucial gap between the clean logical design and the, well, often messy reality of physical deployment. It's where real systems live or die.
Absolutely fundamental.
Second, we underscored the power of horizontal scaling and why load balancers are fundamental for distributing load and improving robustness, plus the nuances of things like session affinity.
And health checks.
And health checks, right. Third, we explored why multi-data center distribution, or multi-AZ, is pretty much non-negotiable for serious enterprise SLA requirements, and how the CAP theorem forces those challenging trade-offs in distributed systems. Can't have it all.
Consistency, availability, partition tolerance, pick two.
We also clarified how database sharing works. It's okay for instances of the same service, but never across different services. And the critical nuances of read replicas handling eventual consistency and replication lag is absolutely vital.
That lag bites people all the time.
We then delved into the cost versus isolation balance of shared versus dedicated database infrastructure, especially highlighting how cloud-managed services like AWS, RDS, really change the economics and feasibility of the dedicated approach.
Makes dedicated DBs much more accessible.
And finally, we talked about the critical role of environment progression balancing cost versus fidelity, and why externalized configuration is essential, not just for good practice, but for actually passing those senior interviews. Don't bake config into your builds.
Build once, deploy many times, externalize that config.
That really covers the core deployment patterns.
Yeah, and understanding these patterns isn't just about memorizing facts, right? It's about developing that senior engineering mindset, thinking through the why behind the choices, understanding the complex trade-offs involved.
Right.
You're not just designing theoretical systems on a whiteboard. You're thinking about how to build systems that actually work, stay up, and remain resilient in the messy real world.
So maybe the final thought for everyone listening is, the next time you look at a simple microservice diagram, challenge yourself. Ask, what unseen layers of complexity, what infrastructure, what resilience patterns are really hiding behind those clean lines? How would you design for them, not just draw them?
That's the key question.
If this deep dive helped you feel maybe a bit more confident for your next tech interview, definitely hit that like button. Please subscribe for more deep dives into critical engineering topics like this one.
Yeah, we appreciate the support.
And share this episode with other engineers who might find it useful. We'd also love it if you'd leave a comment below. Tell us your biggest aha moment from today, or perhaps pose a question you'd like us to tackle in a future deep dive.
We really do read those comments.
We absolutely do. Thanks for tuning in.